Welcome back. The objective of this video is to introduce and apply Cramer's rule. So far you've studied three methods for solving systems of linear equations: substitution, elimination with equations, and elimination with matrices. We'll now study one more method, Cramer's rule, named after Gabriel Cramer. The rule uses determinants to write the solution of a system of linear equations. Let's take a look at a generic set of linear equations here, where we have ax1 plus by1 equals c1. Well, we can write that, and then a2x plus b2y equals c2. Well, we can write that given a coefficient matrix with just our coefficients, where the determinant of that is simply the matrix a1, b1, a2, b2. So easy enough to do the 2 by 2 determinant there. What's new here is d sub x, or the determinant sub x probably. And what we've got here is we replace our x values in our matrix with our constants. So instead of having our a1, our coefficients on x here, that becomes our constant, where our coefficients on y stay in there. Conversely, dy, that one we replace our y values with our constants and keep our x values. So we've got some 2 by 2 matrices here that we'll work with. So in a real system, 2x minus 5y equals 3 and negative 4x plus 3y equals 8. Our coefficient matrix, super easy to see. 2, negative 5, and negative 4, 3 are our two rows. Where d is just the same thing, we could calculate the determinant, multiply 2 times 3 minus a negative 4 times negative 5. Well, d sub x is we replaced our x values. We replaced 2 and negative 4 with our constants 3 and 8. But we kept our y's the same. So we've got constants for our x's and then our y's. Whereas d sub y, our x's stay the same, and our y's become our constants. So as we prepare for Cramer's rule, we look at this 3 by 3 or even larger matrix, and we've got this generic rule here. So if we were solving for x sub 3, so if we're solving for our final variable, it's the determinant of a3, meaning we would replace all of our coefficients on our final value here with our constants while keeping our first two variables and calculating that determinant in our numerator, all divided by the determinant of the coefficient matrix, d. If we were solving for x3, we did determinant of dx3, all divided by the determinant. And that leads us to Cramer's rule. In Cramer's rule, we can solve a system of n linear equations in n variables, has a coefficient matrix A with a non-zero determinant A, then the solution of the system is x sub 1 equals the determinant of a sub 1 over a, where x sub 2, the determinant of a sub 2 over a, and so forth. So in our examples, we've been using dx1 and dx2, where the ith column of a to the I is the column of constants in the system of equations. If the determinant of the coefficient matrix is 0, then the system has either no solution or infinitely many solutions. So generally speaking, to use Cramer's rule, the denominator is the determinant of the coefficient matrix, and the numerator is the determinant of the matrix formed by replacing the column corresponding to the variable being solved for. So if we're solving for x, we would replace our x column with our constants, or d sub x. If we were solving for y, we would use d sub y in our numerator. So let's take a look at a sample using Cramer's rule. So we've got a 3-variable system of equations, which is going to create a 3 by 3 coefficient matrix. Our constants in our first row would be 1, our constant in our second row is 0, and our constant in our third row is 2. D sub x we would replace our x values, or the first column, negative 1, 2, and 3, with our constants. We take our constants, we would put them in that row. That's going to be d sub x. D sub y, we would take our constants and we put them where our y's would be. So d sub y would be the matrix negative 1, 2, 3, and then our constants 1, 0, and 2, and then our z coefficients negative 3, 1, and 4. And then d sub z, same, where we would take our constants and we would replace the z values with our constants 1, 0, 2, and that's what we have done. So we've got our constants and our x coefficients and our y coefficients. So we're going to need those three matrices in order to solve our system. So the first thing we want to do is find our determinant of our coefficient matrix, D. So essentially what we're going to do here is we're going to start with the denominator for Cramer's rule. And we've decided to expand along the second row. Our first term, we're going to use the 2, but our second row, our signs are negative, positive, negative. That's why we have negative 1 cubed, because that's our negative, that's our positive, and negative 1/5 is our negative. So using the 2, we calculate the determinant of our 2 by 2, which is negative 4. So we have negative 2 times negative 4. Continuing across the second row, our second term, our second column here is 0. So 0 times all this is all going to become 0. So that one's nice and easy. And then the final one, we grab our 1, bring that down. It's going to be negative 1 to the 5th we use. And then our new 2 by 2 matrix, negative 1, 2, 3, 4. We calculate that. That's just negative 2. So we have negative 1 times negative 2. And we get a determinant of 10. To solve for our x's, y's, and z's, we've calculated d. That's going to be 10 for all of our x's, y's, and z's. But now we need to find the determinant for x. So d sub x is this particular matrix. I have placed that in there for us. And I've decided to expand across the second row again. So our signs are negative, positive, negative. But since these two values are 0 right away, the only one I have to do is the third column here, because these first two are 0. So my coefficient is 1. My sign is going to be negative, so it's going to be negative 1. And my 2 by 2 matrix, 1 times negative 4 minus 2 times 2, which is just negative 4 minus 4. So negative 1 times negative 8 is positive 8 over 10. 8 tenths, 4/5. X is 4/5. To solve for y, I grab my matrix dy, all divided by d, which is 10, because we figured that out earlier. And I have chosen to expand this across the second row. I don't know if that's the best choice or not, but I have. And so I will do that. I'll figure the determinant of this particular 3 by 3 matrix. So my first coefficient, my first column on the second row is 2, so I brought my 2 in. That value is going to be negative, so our sign is negative, so negative 1 cubed. And my new matrix then is 1, negative 3, 2, and 4. 1 times 4 minus 2 times negative 3. We get times 4 times 4 plus 6. So we get negative 2 times 10 is negative 20. Continuing to expand across the second row, I have 0, so I don't have to worry about that second column. And the third column, it's 1. That sign is going to be negative, so negative 1 to the 5th. And then my new 2 by 2 matrix, negative 1, 1, 3, 2. I've written that here. And we find the determinant of that 2 by 2. Negative 1 times 2 is negative 2. Minus 3 times 1. So negative 1 times a negative 5 is a positive 5. Negative 20 plus 5 is negative 15. So my numerator is negative 15. My denominator is still 10. And I get negative 3/2 for y. And finally, calculating z. My denominator is still 10. That hasn't changed. dz is another 3 by 3 matrix carried over from earlier. I'm going to expand this across the first row. So my signs here are going to be positive, negative, positive. Expanding across the first row, my coefficient here is negative 1. It's got to be positive, so negative 1 squared. And then my remaining matrix is a 0, 0, negative 4, 2. So this all is going to be 0. My first term in determining that is 0. Working down the page, since I ran out of room, my coefficient in the second column, I'm going to use that as 2. Grab that 2. That sign is going to be negative, so negative 1 cubed. And then my new matrix is 2, 0, 3, 2. Calculating that determinant, I get 4 minus 0, so negative 2 times 4 is negative 8. So right now I have 0 plus a negative 8. And then finally doing the third column, my coefficient is 1. That sign is going to be positive. Negative 1 to the 4th power will be positive. It's going to be 1 times whatever my determinant is, which is the matrix 2, 0, 3, negative 4. Negative 8 minus 0 is negative 8. Times 1 is negative 8. Adding up 0, negative 8, and negative 8, I get negative 16. So negative 16 tenths is negative 8 fifths. So my z value is negative 8 fifths. And we have solved that system of equations. X is 4 fifths. Y is negative 3/2. Z is negative 8 fifths. Our final sample is using Cramer's rule to solve a 2 by 2 matrix. This actually is going to be easier than the 3 by 3. My coefficient matrix is 4, negative 2, 3, negative 5. Calculating the determinant of our coefficient matrix is negative 14. That is going to be our denominator in Cramer's rule. D sub x, we replace our x values with our constants, put those in to our constants. So here we have it, 10, negative 2, 11, negative 5. It's a 2 by 2 matrix. Calculating the determinant is easy. 10 times negative 5 minus 11 times negative 2. We get negative 28 over negative 14. So our x value is 2. Our y value is just d sub y over d. Our d is still negative 14. We calculated that earlier. D sub y, now we replace our y values with our constants. So our constants move over and our x values stay the same. So we have a new matrix of 4, 10 and 3, 11. We got to calculate that determinant. 4 times 11 minus 3 times 10. 44 minus 30 is 14. And we get 14 over negative 14, which is negative 1. So x is 2 and y is negative 1. We have used Cramer's rule to solve that system of equations. And you'll get some more practice with Cramer's rule when I see you in class.